What if I told you that rewriting your core analytics engine in this blazing fast systems language could actually slow your entire architecture down by like 1,300 times?
Oh, yeah.
And the crazy part is it has absolutely nothing to do with the quality of the new code itself.
Right, which is just such a paradox. I mean, we are constantly sold this idea that adopting a language like Rust will instantly solve all our performance bottlenecks.
Exactly, the whole rewrite it in Rust meme.
Right. But the moment you take that new ultra-fast engine and separate it from the rest of your system, like putting it behind a network boundary, you introduce this massive new variable that, frankly, most architects completely misunderstand.
Which brings us to our mission for you today. Welcome to this deep dive into a really brilliant piece of research from the Backtests Without Illusions series. We're going to unpack the actual mathematically measured IPC tax.
Right, the inter-process communication overhead.
Exactly. What happens when you put a computational engine behind a socket?
Right.
We're going to find out if the tech industry's folklore about IPC overhead is actually rooted in reality, where those lost CPU cycles genuinely go, and, when crossing a process boundary actually finally pays off.
Because the findings reveal that almost everything we collectively assume about this tax is wrong in general. And this is key, it's devastatingly right under very specific, highly common architectural conditions.
Yeah, so let's set the stage for you. The researchers ran a highly controlled experiment. They took a backtest kernel specifically, this 150,000 bar Python program optimized with numba for, maximum speed, and they ported it line for line to Rust.
Same loops, same math.
Same exact structural logic. Then they tested calling that engine across a process boundary in multiple different ways.
And what's fascinating here is how they began. Because before they even looked at a stopwatch, they built a strict equivalence gate. They ran 80 different combinations of parameters through both the Python engine and the new Rust engine to guarantee the outputs were mathematically identical.
And when we say identical, I mean identical down to the exact decimal point. A PNL of exactly negative 5165.58 across exactly 57,029 trades. By proving that byte-for-byte equivalence first, they isolated the variables.
Right, because a cross-language port is exactly where silent bugs love to hide. I mean, a fee applied in the wrong order or like a slight floating point rounding error can wildly change financial results.
Absolutely.
If the two engines aren't computing the exact same thing, it's not a valid benchmark. It's just two totally unrelated programs racing.
Yeah.
So with equivalence proven, we know we're comparing apples to apples.
So we have a mathematically sound baseline. Let's look at the first comparison. The baseline is just calling that Python numba code directly, right? In process, no network boundary. Yeah. That took 2.010 seconds for the entire sweep. Then, they set up the first alternative, which was a Rust server, bashed via a Unix socket. So this means they shift the entire historical data series and all 80 parameter sets in one single payload over the boundary.
One big chunk of data.
Exactly. Okay, let's unpack this because the result just completely flips conventional wisdom. The batched Rust server took 2.276 seconds.
Wow.
Yeah, it was roughly 13% slower than the in-process Python baseline. Now, standard tech folklore insists that this 13% slowdown is the IPC tax, right? The literal cost of sending data over a socket.
Right, everyone blames the socket.
But the researchers actually measured the boundary transit itself. Shipping that 1.2 megabytes of data over the socket only took about 2 milliseconds.
2 milliseconds out of a 2-second job. I mean, that is roughly 1/10 of 1% of the total execution time. The boundary transit was practically invisible.
That is highly counterintuitive. If the delivery mechanism only took 2 milliseconds, that leaves this massive, 266 millisecond delay entirely unaccounted for. It means the naive Rust code simply computed the math 13% slower than the Python code. We can't really blame the network tool booth if the factory itself is just slower at building the product,
The factory analogy captures the reality perfectly. I mean, we intuitively blame the delivery driver, the socket, because it's the visible boundary between systems. But to understand why the Rust factory was slower, we have to look at the underlying machinery.
Right.
Both of these languages, in this specific context, bottom out in the exact same place, which is LLVM.
So for you listening, LLVM is essentially this compiler infrastructure. It acts like a universal translator, right? It takes the high-level code from Python's numba, or the Rust compiler, and turns it into the exact same low-level machine instructions for your CPU to execute.
That's the core of the issue. Numba lowers its bytecode to LLVM intermediate representation, and the Rust compiler does the exact same thing. So we aren't really measuring Python the language versus Rust the language. We are measuring a code generation gap between two sets of LLVM compiled instructions.
Right, so since it's all translating down to the same machine language anyway, simply stamping Rust on the box doesn't magically make the math compute faster.
Exactly.
But surely the researchers didn't stop there. If Rust was slower, did they try to figure out why and optimize it? For instance, I know Rust has mandatory bounds checking on arrays to prevent memory leaks and security vulnerabilities.
Right, which Python's numba actually turns off by default in this specific mode.
So did they test a version without those safety rails?
They did exactly that. They created a new architecture, a variant using a get-unchecked kernel. This explicitly bypassed Rust's bounds checking under the very logical assumption that, checking the length of the array on every single iteration of a 150,000 bar loop.
Was the anchor dragging down performance?
Yes, exactly.
That makes perfect sense on paper. Remove the safety checks, speed up the loop.
Yeah.
So did it close the 13% gap?
It actually widened the gap.
Wait, really?
Yeah, the get-unchecked architecture was even slower. It came in at 2.337 seconds.
That is fascinating. If explicitly removing a safety check actually slows the code down, it means we can't just rely on language syntax to save us. We're entirely at the mercy of the compiler's black box.
We truly are. When dealing with modern compilers like LLVM, removing a bounds check can unpredictably alter how the compiler analyzes the loop. It might change its instruction scheduling.
Like the exact order it feeds operations to the CPU pipeline.
Exactly. Or it might fail to unroll the loop as efficiently as it did before. Without deep assembly-level profiling, it just remains this unattributed gap. The crucial takeaway for you is that porting to a systems language buys you a deployment boundary, but it guarantees absolutely nothing about raw compute speed until you actually measure it.
Which brings us to a major pivot in this deep dive. If the socket itself only takes 2 milliseconds, which is a literal rounding error, why does IPC have such a terrifying reputation in the industry?
Right.
If the boundary is cheap, the folklore has to be coming from somewhere.
The folklore comes from how developers typically choose to cross that boundary. The tax isn't inherent to the socket itself. It is entirely self-inflicted by architectural choices. The research highlights several massive pitfalls, which we can categorize as the sins of deployment.
Okay, the first sin is the serialization tax, and the numbers here are frankly grim. The researchers measured the cost of encoding the 1.2 megabytes of data to cross the socket. When they shipped it as raw binary bytes, the encoding took 49.1 microseconds.
Yep.
But when they encoded it as a standard JSON payload, which is, the default language of nearly every modern microservice, it took 66 milliseconds. That is a 1,348 times penalty.
The sheer scale of that inefficiency is just the hidden killer of distributed systems.
It's like taking a beautifully organized bound encyclopedia, shredding it into individual letters, mailing those letters in separate envelopes, and making the receiver painstakingly glue it all back together into pages just to read it, just send the book. Why does converting to JSON incur such a massive penalty?
Because of what JSON fundamentally requires the machine CPU to do. When you serialize a large array of numbers into JSON, you aren't just pushing memory from one place to another.
Right.
The system has to allocate new heap memory space for every single floating point number. Then it has to look at the raw binary math and render each 64-bit float into human-readable UTF-8 text characters. You are executing 150,000 separate, complex string conversions.
Just to have the server on the other side parse that text right back into binary math to do the actual calculation.
Exactly. And that 66 milliseconds they measured was just for one side of the transaction on a single call. If you are running a service that constantly communicates using JSON, the client-side encoding alone can burn over 5 seconds on a job that is only supposed to take 2 seconds in total.
Wow.
The text protocol itself becomes an artificial crushing bottleneck.
So the architectural rule here is absolute. Speak binary. When shipping arrays between processes, use raw bytes or a specialized in-memory format like Apache Arrow, which is designed specifically to move data between systems without needing any decoding.
Never use text protocols for heavy math.
Right. Now, even if you do everything right and send raw binary instead of JSON, you can still bottleneck your system if you send those raw bytes too often. Which brings us to the second sin, the chatty versus chunky dilemma.
Yes. This is often tied to Martin Fowler's first law of distributed object design, which essentially states do not distribute your objects, but if you must cross a boundary, you do it coarsely.
The researchers tested this by altering their architecture again. We know the chunky badged version shipped the whole data set once and took 2.276 seconds. So they built a chatty Rust server. Instead of sending all 80 parameter combinations at once, it shipped the 1.2 megabyte data set 80 separate times, once for every single parameter combo.
Right.
That chatty architecture took 2.383 seconds. It was roughly 1.19 times slower than the baseline.
If we connect this to the bigger picture, an extra 107 milliseconds might not sound like an absolute disaster for a 2-second job, but that penalty is entirely voluntary, and it exposes the real flaw in most distributed architectures, which is statelessness.
So, because the service is designed to be stateless, it essentially has amnesia. It forces the client to resend the entire 1.2 megabyte historical dataset for a payload that realistically only required a tiny, 48-byte parameter change.
That is exactly the core of the bottleneck. A stateless service pretends every request is the first time it has ever met the client. It is the default posture of almost every REST API ever designed. But the researchers showed that if you change the architecture to be stateful, meaning you preload the heavy data series into the server's memory just once, and then only send the 48-byte parameter changes on the subsequent calls, that chatty penalty completely vanishes.
Oh, wow. The overhead drops from 107 milliseconds to about 1.3 milliseconds for all 80 calls combined.
Yep.
The lesson is that making multiple calls over a socket isn't inherently evil. The evil is repeatedly shipping the exact same heavy state because your protocol refuses to remember anything, preload the data, ship the parameters.
Right, that covers the network side. But there is a third sin, which happens when developers decide to avoid long-running servers entirely.
The spawn cost. This is the final architecture pattern they tested. Instead of keeping a Rust server running, they just spawned a new instance of the Rust binary for every call, piping the data through standard input and output.
Which is incredibly common in data science workflows.
Yeah, or hyperparameter tuning frameworks, where they just shell out to a command line tool from Python.
It's a very easy instinct for developers, but the researchers measured this approach at 2.300 seconds. It added a fixed 24 millisecond cost over the persistent server.
What exactly is happening at the operating system level that burns those 24 milliseconds? Because that seems incredibly slow compared to a 2-millisecond socket transit.
It comes down to the heavy lifting the operating system has to do to birth a completely new process. When you spawn a binary, the OS has to execute a fork and an exec system call. It has to carve out brand new memory blocks, set up page tables, invoke the dynamic loader to link all the required system libraries, copy over environment variables, and tell the CPU scheduler to context switch and wake up this new entity.
That is a lot of work.
And when the job is done, it has to tear all of that down and clean up the memory. That is massively heavier than just pushing bytes down an already open socket tube.
Which means if you only incur that 24 millisecond spawn cost once for the entire 80 combination sweep, it's just noise, right? It's barely 1% of the wall time. But if an engineering team accidentally designs a workflow that spawns a new process for every single parameter combination,
then you face an arithmetic disaster. 80 combinations multiplied by 24 milliseconds is nearly 2 seconds. You would spend your entire useful compute budget just asking the operating system to create and destroy processes.
Right.
You are essentially building a massive new factory, manufacturing a single bolt, and then immediately bulldozing the factory to the ground.
Okay, so we've mapped the pitfalls. No JSON serialization for arrays, no stateless amnesia forcing data reships, and no bulldozing the factory by spawning a process per tiny unit of work.
But how does a system architect actually calculate if their specific real-world deployment pattern will survive crossing this boundary? To calculate that, we have to establish the absolute latency floor of the transport. The researchers tested this using what they called the echo curve.
Here's where it gets really interesting. They sent smaller and smaller payloads back and forth over the Unix socket to see how fast a round trip could possibly be, stripping away the compute time entirely. And they hit a hard physical floor. A tiny payload essentially just knocking on the server's door and coming right back bottoms out at exactly 14 microseconds.
That 14 microsecond floor is the irreducible price of making a call over a Unix domain socket on a single machine. It consists of the kernel overhead.
Right.
2 write system calls, 2 read system calls, traversing the kernel's network stack, and the time it takes the CPU scheduler to context switch and wake up the receiving process. Below a certain data size, you aren't paying for the weight of the bytes you send. You are just paying the baseline toll booth fee for the privilege of making the trip.
It is the cover charge, just to get into the club. You pay it no matter what you do once you're inside. And that floor dictates your hurdle rate. A call across the boundary is only logically sound if the compute work you are sending clears that 14 microsecond hurdle by a massive margin.
The researchers formalized this concept into a mathematical ratio, the granularity ratio, which they denote as G. It is wonderfully simple. G equals the compute time per call divided by the latency floor.
So let's actually run the numbers for you. In their specific backtest sweep, computing one single parameter combination took about 25,130 microseconds of raw processing time. If we divide that compute time by our 14 microsecond latency floor, we get a G ratio of roughly 1795.
Meaning the actual useful work taking place is nearly 1,800 times larger than the fixed cost of crossing the boundary.
With a ratio like that, the architecture is incredibly safe. The boundary claims less than 0.1% of your total time. You clear the floor effortlessly. But this ratio becomes a diagnostic weapon when you evaluate different system designs. For example, what if a team refactors a legacy system to stream live tick data instead of doing a historical sweep? They design it to poll the engine bar by bar, 150,000 separate times as the data trickles in.
Well, under that highly granular architecture, the math turns entirely hostile. The compute work required for just one single bar of data is microscopically small, about 0.17 microseconds.
So 0.17 microseconds of compute divided by the 14 microsecond toll booth floor, our G ratio plummets to less than 1.
Far less than 1. It is dead on arrival. If you force the system to make 150,000 separate calls that each incur 14 microseconds of baseline overhead, you are paying 2.1 seconds of pure IPC tax on a job that only required 2 seconds of actual compute.
Ouch.
The tragedy here is that it would still take 2.1 seconds, even if the Rust engine on the other side was infinitely fast and computed the math in 0 time.
Because no compute advantage in the world survives a granularity that fine. You cannot optimize your way out of a bad G ratio. But this makes me wonder, are we stuck with that 14 microsecond floor forever? Is that just an inescapable law of physics for inter-process communication?
Not at all. That 14 microseconds is simply the cost of the specific transport they chose, which was a Python client talking to a Unix domain socket mediated by the OS kernel. The transport mechanism itself is an architectural choice.
So if you change the transport, how low can the floor actually go?
The researchers highlighted another transport mechanism they developed called ZigBolt. Instead of routing traffic through standard kernel sockets, ZigBolt uses a shared memory ring bus. Both processes literally look at the same physical piece of RAM in user space to pass messages, bypassing the kernel entirely. When they benchmarked that on the same machine, the round-trip latency floor dropped to roughly 39 nanoseconds.
Nanoseconds. 39 nanoseconds compared to 14 microseconds, that is roughly 360 times faster.
It drops the floor by nearly 3 orders of magnitude, and when you drop the floor that dramatically, you completely rewrite the break-even arithmetic.
I see where this is going. Because if the floor is only 39 nanoseconds, then even that hyper-granular per-bar live stream we just talked about, the one that choked the system for 2.1 seconds on a Unix socket, suddenly clears the hurdle. 150,000 calls multiplied by 39 nanoseconds is only about 6 milliseconds of total overhead.
Which is precisely how ultra-low latency and high-frequency trading systems can afford to cross-process boundaries that a standard REST microservice cannot. The break-even arithmetic, the G ratio, stays exactly the same. You just artificially lowered the hurdle by choosing a transport built purely for same machine speed rather than network compatibility.
So what does this all mean for you, the system architect listening right now? The operational mechanics are crystal clear. Cross the boundary, coarsely batch your work so your G ratio remains high. Speak binary, or use formats like arrow to dodge the serialization tax entirely. Preload your heavy historical data so your server is stateful. And above all, mathematically verify your compute advantage before you just assume that a new language is inherently faster.
Those are the operational rules.
Yeah.
But this raises an important question. If crossing a boundary requires this much careful arithmetic and structural discipline, why endure the headache at all? Why not just stay comfortably in process with Python and numba forever if it is already fast enough?
That's the million-dollar question. If you don't need the speed, why buy the boundary?
The ultimate answer is parity. If you keep your engine in process for research, but your live trading system runs in a different language or environment like C++ or Rust, those two code bases will inevitably drift apart over time. You will accumulate silent logic bugs. Your Python backtest might tell you a strategy makes millions, but your live Rust trader loses money because of a minuscule discrepancy in how a fee was calculated, or how a missing data point, like a NaN value, meaning not a number, was handled by the two different systems.
The silent killers of quantitative finance.
The data backs that up. By putting a single compiled kernel behind a well-designed process boundary, you guarantee that your research sweep and your live trading loop run the exact same binary, the same arithmetic, bit for bit. This study proves that if you architect the boundary correctly, paying 0.1% of your wall time for that guarantee is an absolute bargain.
It acts as a structural cure for logic drift. You trade the complexity of a dedicated process boundary in exchange for absolute one-kernel parity.
Done right, it secures your architecture. Done wrong, you inadvertently deploy a 1,300 times serialization tax to production with your core revenue stream riding on top of it.
Which leaves you with a final thought to mull over today. If both the Python code and the Rust code in this study ultimately translated down to the exact same LLVM machine instructions, and the actual transport cost of crossing a process boundary is practically a rounding error when engineered correctly, is the tech industry's ongoing obsession with constantly rewriting in a faster language actually blinding us to the real bottlenecks?
It is a vital question for any engineering team to ask.
Perhaps the future of ultra-low latency architecture isn't about endlessly debating the syntax of the right programming language at all. Maybe the real frontier, the place where the architectural battle is actually won or lost, is in mastering the engineering of the boundaries between them.